All right, so in this video, we want to talk about how projections can affect the variance. So I've got here some data, very easy data that's spread out here. By the way, right now we haven't mean subtracted the data, so but that will be coming later. Now, suppose that I've come up with some different vectors u that I want to perform a projection with. So in this case, right, I would project my data orthogonally, right? And then this data now, in terms of the scalar values along here, scalar projections, I could compute the sorry, let me spit that out again. I could compute the variance along that direction. And similarly, if I have my data sitting here, I could, take maybe a vector in this direction, and then that would project my data here, right? And I would be able to figure out a different projection. So is the variance going to be different? I wonder. Depending on the direction. Well, you can see something bad happens, right? If I happen to pick a projection to this vector, right? Because that projects everything to one point, and the variance has vanished, right? And similarly, I could project down here, and that doesn't look like in this case, this is just a particular data set, but in this case, it looks like this is a direction where the variance hasn't changed at all. Okay, so our question then is, how does the variance change with the projection? So how does the variance change with projection? How does variance change with projection? So just like the last video, I've got my P data points. Each of those are in Rn, and I choose a vector u, and I look at the projection, the scalar projection. So now I've got some new data. I'm going to reverse this. I'm probably going to reverse this in a second. But now I've got a bunch of scalar data, right? This is scalar data that I can work with, and I want to find the variance of this. Okay, so the variance is easy. So let's see, what will we call it? Variance in the direction of u. Okay, that's 1 over p minus 1, sum k equals 1 to p of xi transpose times u minus the mean. Do you remember what the mean is? Yeah, the mean is the projection of x with u. Okay, and so I can factor out the u if I would like. Oops, I need to square that. But you know what? What's going to make this simpler is if we assume that the mean is 0, because that's easy to do, right? You take your data and just mean subtract it before you use this formula. So assuming mean 0, this becomes 1 over p minus 1. Let me reverse that too. I don't know why I started with xi transpose k equals 1 to p. Just the notation will look a little bit easier. U transpose times xi squared. Now, that's just squaring a scalar, right? So I can square that any way I want. So I'm just going to rewrite that as U transpose xi. But I'm going to reverse the dot product because I can. Right? You can reverse the dot product, doesn't change anything. And notice that this is a scalar and this is a scalar, the same scalar, right? So that's the squaring just becomes this product. And do you see where I was going with that? The u factors out the front, and this u factors out the back, or I guess, well, whatever. And then you're left with the sum k equals 1 to p of xi transpose times u. This is a very interesting, very interesting expression. Why? Do you see it? What is this thing right here? That is the covariance matrix. So what we're saying is that the variance of my data projected to U is equal to U transpose times the covariance matrix C times U. Just double check, make sure that this is the right thing here. U is a vector in Rn. So what are we looking at here? U transpose is 1 by n. The covariance matrix is n by n. And U is n by 1. So we are looking at a scalar, right? This is a scalar value. Good. And so you can see right away the variance of the data projected to a vector U is U transpose C times U. Very nice. So the covariance matrix will tell us a lot, right, about the variance of the projection in lots of different directions. So what happens if U is an eigenvalue of C? So then, what does U transpose U become? Yeah, C times U is just lambda times U, right? So that's going to be equal to lambda times U transpose U. What's U transpose U? That's equal to 1. And so in that case, the variance is equal to lambda. So the eigenvalues, the E values of the covariance matrix tell you what the variance is in the direction of the eigenvectors. So this is the variance in the direction of the, am I right, still on the screen? EVEX. Right, so if this was U1, this would be lambda 1. If this was U2, this would be lambda 2, and so on. Very nice. Boy, that's a beautiful result. Maybe you learned it in statistics, I'm not sure. So this is going to actually play a kind of a key role in our construction of the error. So if you're following along, what's next is going to be the reconstruction error that we're going to use for the best basis. So whenever you're talking about something being the best, right, that must mean that it minimizes some quantity. And so what we want to do is try to figure out what the error is. So what is the error that we're going to be using? Error for the best basis. Okay, so we're looking for an error function, actually, the error function for the best basis. Well, I can tell you quickly, symbolically, what it's gonna be. If I've got a bunch of data in, let's just say these are in Rn, right? And I've got a subspace K, a k-dimensional subspace. Right? Then I can write each point xi, right, as a point in the k-dimensional subspace, right, plus a point that's orthogonal to that subspace, right? And so this is going to be the error for xi, this length right here, the distance between the projection and the original data point. Okay, so the error is going to be the sum of those. It's going to be the average of those. So the error is going to be the average of the error. That's going to be the sum of the projection of x onto your subspace. Let's say the subspace band by some columns of U. And what? And xi, what is this? So this is the projection, xi minus the projection, right? Minus x minus the projection. Oops, what did I do there? I didn't want to make that. This should be just the x minus the projection, right? Squared. and I'm summing those over all my data. So we just need to figure out what does this function look like. Good. So let's see, I'm right at the 10-minute mark, so I think I'm going to stop here and we'll do the whole thing in the next video. See you then.